AB calculus lesson, continuity and IVT. Here's a warm-up, guys. So why don't you pause the video and see if you could do these, okay? All right, guys. I will assume that you've already tried this, and if you have not, pause the video again, okay? All right, guys. So here are my answers. Looking at this picture, F, G, and H at 2 are not D and E and J at the same time because this jump discontinuity here, and at J, oops, I forgot to graph that thing. So when it's left of 2, it is 1. To the right of 2, greater than or equal to 2, it's a 0, right? So that's jump discontinuity right there as well. I spoke a little bit too soon earlier. For H, though, if you simplify this, the x minus 2 cancels, and x cannot be 2, obviously. So there's a little hole right there, guys, right? But because they're pointing at each other over here, the limit does exist, and the value is indeed, oopsie, that must be 4, okay? All right, so if you just do this for, let's say, G and H as it goes to 2 is D and E, because when you're coming from the right-hand side, it adds up to 4 and 5. So let me go through this one a little kind of carefully. So if you look at G, which is this one right here, guys, right? When you're coming from the right-hand side, it's approaching 0. That's what I have over here. For H, whether you come from the left or the right, my value here is 4. Okay, so that's what I have. So this is 4, even though it's coming from the left. If you look at the G of X, however, it is different. It is 1. So the value is different. So if you go to the same argument for these 3, you'll find out that the left and the right match. Hence, their limits are 1, 0, and 0. Okay? All right, guys. So we have the first page. Okay? So our objective is to define continuity and to find out where it is discontinuous and to introduce the IVT, intermediate value theorem. Okay? So definition number 1, a function f is continuous at a number if, number A, if the limit from both sides, that's two-sided, guys. Just remember that. This is two-sided. That implies the limit from the left is indeed equal to limit from the right, and that actually has to equal to f of a. So that is the implication right there, guys. Okay. So what that basically means is the graph that you see over here is that coming from the left and the right, the limit is the same, and the value at that a is indeed equal to the limit. If that happens, we say that the function is continuous at this particular point a. So this definition prevents you from happening the 3 other possible discontinuities: removable, otherwise known as a hole, infinite, otherwise known as asymptote, and jump. Okay, so this is a way to ensure that. So when you say that, when you read that as it has a 3 implicitly things are implicitly said, right? Number 1, f of a is defined that there's a value over here, right? And the value exists. And then that tells you that it's a two-sided continuity. And then by having the last statement, it prevents you from having a hole, right? So I basically wrote out what I verbally said. Okay? All right, guys. Let's have an example over here. It's usually a good idea for you to sort of pause and try this on your own if you can, right? Or you could just listen along. It's completely up to you. And let's examine where things are. So we got stuff over here. That's x equal to 1. Okay. When x equal to 1, it is discontinuous because there's a hole. The value, actually, there's a hole, but more importantly, the value doesn't exist because f of 1 does not exist. So the reason number 1, right? You actually want to say that specifically. So what is it when, let's go with different color. How about here, guys? So x is equal to 3. So when a is equal to 3, what happens? Okay, the limit as x goes towards the a, f of x is dne, or what you could have said instead is that the left and the right limit is different. Okay, left and the right is indeed different. Let me make that a little smaller so that will fit a little better. There you go. Okay, so in other words, that's what that means, right? And the third possibility is when a equal to 5, there's a discontinuity because of the reason number 3. Even though the limit, let's go with a different color here again, when it's equal to 5, it's pointing at the right direction, so the limit does exist. However, limit as x approaches 5 of f of x does not equal to f of 5. That is a reason number 3. Okay. All right, guys, let's get going. So there's a page over here, and your job was to sort of work it on your own. But I'm going to just show you the answers right here, guys. So when you do this over here, that is what? X minus 2, x plus 1 over x minus 1. So that is x plus 1 where x cannot be 2. So there's a hole right there, right? So there's a hole. Because of that, there's a removable or hole discontinuity at x equal to 2. And when we draw this picture, we've done this in class already, right? There exists a infinite. The second one that I always put is more of like an informal name that students say. Discontinuity at x equal to 2. And the next one over here is almost the same as this one over here, but it's slightly different in that there's a value that exists right there. Okay. All right. I must have copy pasted it because this is not infinite or asymptotic discontinuity, but rather it is a same thing as the one above. It is a removable, a hole discontinuity, whether or not there exists a value at the point of discontinuity. So we have a value here and one above does not, but it doesn't matter. Okay. And over here, this is jump discontinuity. Let's jump over here, 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 and here, right? That happens whenever the x value is equal to an integer. So that's an integer. So when you're writing by hand, we would just write z with the extra line over there, right? That's a fancy expression for integer. Okay. All right. So let's go through some definitions here, guys. A function f is continuous from the right, if the limit from the right is equal to this. So for example, we may have something that looks like this, right? So from the left, it is not continuous, but from the right, it is continuous. For the second one, maybe you have something that looks like this. Something like that, okay? So that is continuous only from the left, okay? All right. So let's move on to the next page. There's lots of definitions, and many of them are sort of intuitive, but we need to say it in an exact form, right? Make sure to fill in the blanks, okay? So it's talking about the fact that function f is continuous on an interval if it is continuous at every number in the interval. If f is defined only on one side of the endpoint of the interval, we understand the continuous at endpoint means to be continuous from either right or the left. So it's a bit of an extension on the previous idea, right? So I kind of put some implication over here is that there's a little bit more to it actually. Sometimes we do only one side or the other, but sometimes we have something called closed interval, which means that the function is continuous on closed interval if it's continuous in every value in the interval, including the endpoints. If you exclude or not include the endpoints, then we call that the open interval. So example of this might be, that's closed interval, and that is the open interval AB. Okay. And earlier here we're talking about maybe it's to the left or to the right. So whenever there's a bracket, we include that endpoint. And the theorem that says is that more of the continuous theorems, right? If an f and g are continuous at a and c is constant, the following things are true. The sum of the continuous functions are continuous. The difference of the continuous functions are continuous. If you multiply a continuous function by any number, it is continuous. It's a vertical stretch, right? And then the product of it is continuous. It's almost like a limit law, isn't it? But then again, if you think about it, continuity is defined through properties of limit law, hence it has a similar idea. And the quotient of continuous functions are continuous as long as the denominator is not equal to 0. Okay? And some reiteration of things that we suspected to be true, and I believe I mentioned it in the previous class, is that polynomials are continuous everywhere. That is, it is continuous on R. That's the real number. And you would write that like this if you're writing by hand, right? Just with the extra line, extra vertical line. And that is defined to be negative infinity to infinity. I included the interval notation. And any rational function is continuous wherever it is defined. That's a key word, wherever it is defined. So its implication is that whenever it is not defined, it is not continuous. So when is it not defined? If the denominator is equal to 0. Okay? Yeah. So so you have to be aware of the function's domain. As long as it's part of the domain, it should be continuous. Okay. So essential takeaway from part B, right, is that the function is continuous on its domain. So how about the other familiar functions, like trig functions, right? If you look at sine and cosine, it's continuous everywhere. But if you look at tangent and cotangent, like every pi or so, same thing with secant and cosecant. So those are reciprocals, right? And similar will be true for the inverse functions or square roots, right? So for example, if you have, I don't know, 3 minus x, it'll be continuous everywhere as long as it's greater than or equal to 0. So as long as x is less than 3, this function is continuous. The reciprocal functions include trig, by the way, and log functions and exponential functions. So you have to be very, very familiar with its domain and range, right? Good. Okay, guys, this should be almost the last theorem, actually. Almost. The g is continuous at a and f is continuous at g of a. Ooh. Then the composition, right, of f and g is given by this expression right here, guys. So composition f and g of x is f of g of x, right, is continuous at x. So as long as these conditions are met, we're good to go. All right, guys. So let's go to the next page. Oops. All right, here we go. Why don't you take a moment to do the examples over here, right? Please pause the video. Okay, so you're back. Let me show you the answer key that I created for this, right? Part 1. From the graph, state the interval in which this is continuous. So I wrote it out. So it's including negative 4 excluding negative 2, from negative 2 to 2, right? Open interval negative 2 to 2, and including 2 excluding 4 right there, open interval 4 to 6, and open interval 6 to 8. So that's what I did. Part 2a, I find all the points of discontinuity. So whenever there was a jump, I would, or infinite, I didn't see a removable here. So at negative 2, it's jump. At 2, it is a jump. At 6, it is infinite because it's asymptote. And 6 is a jump. So here, because they're both open, it's neither side is continuous. At 2, though, it is continuous from the right side. Well, we could say the right over here, though. I wouldn't necessarily talk about this right here. I didn't include that over here, right? Partly because it was only defined, this function was defined from negative 4, including negative 4, up to, but not including 8, right? With a bunch of exclusions, right? So that's the reason why I didn't include it. But if you had to, you could argue that in its endpoint, that it is continuous on the right-hand side, okay? By the same token, if it's 8, it is not continuous from the left because it's open right here, right? And then if you look at 4, they are neither, and 6, this is a jump, and is neither because they both have this, okay? So this is only one with that. So all the other points that are not part of the discontinuity have, that is continuous from both sides. All right, for this one though, let's take a look at this. You fact out the x, then that becomes a whole at that point, and this image is basically transformation of 1 over x, right? So this right here is removable because if you cross cancel, it creates a whole, right? And then here is a infinite discontinuity because there's a hole over here, so it is neither for both of them, right? In terms of its continuity. And then we cross cancel, we come up with this over here. So it's a straight line with a hole at negative 1, but there's a value that exists that was defined for us at 2. So 1 is removable and it is not continuous in either side. Okay. All right. C. So basically all pieces are continuous within its domain. So we just need to check the endpoints. Its endpoint is where the overlapping part right there is negative 1. Coming from the left, it is 2. Coming from the right, it is 2. And I plugged it in at that point at negative 1, it is 2. So it has met the definition. Therefore, function g of x is continuous at x equal to negative 1. At 2, however, from the left-hand side, it's equal to 5. From the right-hand side, it is equal to 4. So for example, if it can't be 2 over here, right? So you basically plug in a value over here, like 1.999, and then you plug in maybe 1.99999, and you see that it's approaching 5, right? So that's why the limit is 5. If it's actually, do the same thing over here as well, right? Anyways, the left and the right is different, so hence it's a jump discontinuity at x equal to 2, okay? So if you have issues with this, you could post it along in the discussion. It doesn't just have to be a homework question. If you do have questions and notes, and give me a heads up, I might be able to be ready for that. Okay, guys? All right. Okay, in the next page, over here, could you make a correction over here, guys? This right there, okay? That should have been negative 1, okay? All right. So let's begin. So we're talking about the intermediate value theorem, guys, okay? Suppose that function f is continuous on a closed interval a, b, and let n be a real number between a and b. In other words, n is between, right, f of a and f of b. and that'll be the notation that we use, right? The word between means you do not include the endpoint. Hence, the word is an open interval. Then there exists a number C. Some books call it, in some books they'll say at least one C in that interval AB. The keyword is function has to be continuous in a closed interval, but the C has to be in the open interval AV. You gotta be careful, all right? Such that f of C is n. So what the heck does that mean? Okay, so what that means is that let's say we start with this value here, and B is here, let's say. We first say that n is somewhere here. Let's call that n. Y is equal to n, and clearly n is between f of a and f of b. Having said that, as long as the function is continuous from a to b. When I say from, we're starting at a and ending at d. So it could be going straight like this, or it could be like doing something like this, or it could just be going up and down, doing something silly like that. What that means is that in a plain English, right? Because there is a value, as long as we go this way, we have to go up this way, and we have to go through every single value somehow. So that we have to cross n. There's no way for us to jump across it. If you jump, that's just jump discontinuity, isn't it? Hence the requirement, it must be continuous. So potentially you could have a picture that looks like this, or like this, or I don't know, something crazy like that. In any case, as long as you draw a continuous line from A to B, it will have to cross or be equal to the value n that is between f of A and f of B. So that's all that means. In other words, it has to have a value between f of A and f of B, as long as you're going from A to B. That's all that is. So another way to say that, okay, is that the intermediate value theorem states that the continuous function takes on every intermediate value between f of A and f of B. I just said that, right? Right. From the domain, in that domain AB, open interval AB. Okay. All right, guys. Let's see if you could do this. Okay. Try to do this on your own. Pause the video. Okay. So basically, for this particular example, we know that the key word over here is that we know this is this continuous, right? Oopsie. Continuous. All polynomials are continuous over real number, right? So we know it's guaranteed to be continuous. So we know that. So, and it doesn't really matter whether it looks like this or like this. We know it's continuous, okay? So you don't really have to take the time to try to graph it, right, at all, because key thing is that it is continuous. But what you have to do, though, is plug in the 2 into the function over here. So f of 2 is negative 2. So we start here, plug in the 3. What do you get? You get 13. So between the domain value 2 and 3, it takes on every value in the range from negative 2 to 3 here. So they're asking, is there a 0? Of course. What's 0? 0 is right here. Right here, guys. Is that between negative 2 and 13? Yes, it is. Then, by IVT, there exists at least one value of C that is in the open interval 2, 3, or you could just say between 2 and 3, such that my Y value is 0, which is between -2 and 13. That should be an open interval, my bad. Sorry about that. There you go. All right, so you have to state all this, okay? The next one, first one is false because the 0, I'm sorry, so I actually made a mistake earlier. That's not the reason, because I had mistakenly wrote that as a 1, sorry, over there. So that's the way I did it, but it's still wrong, right? It's wrong for a different reason, okay? Basically, the IVT does not guarantee that at 0, there'll be a 0, okay? All it says is that there'll be some value in between -3 and 6 that will be equal to 0. So that's false. So that's not an IVT at all. B is false. It is true though, but not because it's IVT. This is actually something else, okay? It's very kind of similar. It's an extension of intermediate value theorem. If you do, kind of actually. But you have to learn Rolle's theorem first in order to do this. That's the mean value theorem. But let's move on. So C is not true. We know that according to this, it has to be open interval. Okay, hence false. And then f of C for at least 1. So is is f of C, is there value 1 here somewhere? Is that between -1 and 3? Yes, it is. Then you're guaranteed that there is at least one C such that it will cross that point somewhere between -3 and 6. So this is indeed exactly IVT. Okay. Now, if you look at E, it's almost IVT. Actually, it is, because this is 0, which is in between these two values. Then you're guaranteed that there will be something in between these two. But is it really? It guarantees that it's going to be between -3 and 6. It doesn't guarantee that it has to be within shorter interval. It is for that reason. You might have said yes. The answer is no. Because it's possible it could have gone to 0 here like this. It go down and come up this way and avoid -1 and 3. Does that make sense? Good. All right, guys. So the next page is that here's an example of how the IVT can show up in the AP exam. So give it a shot, and I'll go over it in a second. Please pause the video. Okay, so here goes. So first thing I do is we're interested whether or not this exists, HR. So I need to find out what that is at 2 and 5. Those are my endpoints, right? So h of 2 is defined to be this. I plug it in. F of 2 is 5, so that's a 3. So when I do h of 5, this f of 5 minus 5, f of 5 is 2. So what that means is that my y value goes from -3 to 3 when my x is between 2 and 5. So if you had to draw a picture here, guys, right, it's a 2 and a 5, and it goes from -3 to 3. All the IVT says is that it starts from here to here. And what value are we interested in? 0, here. At some point, it says it will pass, whether it's going to be like this, or whatever. It has to go through that at somewhere between 2 and 5. Is that true? Of course it is true. Because first of all, they're saying that, well, we haven't learned this yet. If it's twice differentiable, all right, it implies continuity. Okay? The function is continuous here. Because that is continuous, because that's actually polynomial, right? The difference of the continuous function is continuous. So that is continuous, right? So we know that. So we know that h is continuous from 2 to 5. Therefore, it contains, so that it must go through any value in between. So by IVT, given that the n is between negative 3 and 3, there exists at least one c in 2 and a 5 such that f of c is n. So I just stated IVT pretty much word for word in a slightly different way. But we know that the n that we're looking for here, guys, right? Right here is between negative 3 and 3. So this is the part that is the answer, right? Since n is between that, by IVT, there will be r, right? Between 2 and 5, where h of r is 0. That's the n, right? That's the n. And then we're done. And the last one is a little tricky, actually. So you have to sort of create a situation. To say that the c squared is 2, that is some sort of a function, right? So f of c is equal to 0. So more generally speaking, we talk about f of x equal to x squared. So we could choose any arbitrary interval. Let's choose 1 and 2, okay? Because we want it to work, okay? So f of 1 is 1, f of 2 is 4. So from here to here, because I chose it so that it's just that there is a positive value c such that that must be true. So you just have to say that there is a interval, right? So you just have to choose an interval that actually has the answer, right? So I chose 1 and 2 because I know that 2, when you square root of it, is between 1 and 2, right? Well, anyways, so we know that x squared is continuous over r. I'm sorry, I don't know how to say of. That should be over r, or negative infinity infinity. By IVT, there exists at least one c in that interval right here, where this f of 2 is 2 is between 1 and 4. Okay? Okay, that is it, guys. And if you have any questions about it, post it in the Canvas, and I will be sure to address that in class. All right, guys. See you in class.